You have an exam on Thursday. The content that is fair game for the exam is day 1 through last Thursday. Today we're talking about protein function. So the material or the skills that we'll be exercising today won't be on the exam. Although some of the stuff we'll do today, you'll see is an application perhaps of some of the things we talked about in the past, but you don't have to worry about this necessarily. But who knows, you might notice that it may help you study, which is always good. On Thursday, I'll give you the option to begin testing, or the option to begin testing at 9 a.m. So if you want to take the shuttle early to be here by 9, I'll hand out exams and start the clock then. You'll have until whatever the end of class is today, which I think is 10:30. So you'll have 9 to 10:30, so an hour and a half instead of an hour and 15 minutes. So I've made a note of that. I've made a note on my calendar. So just a reminder that is the case. Also, don't forget your calculators. So in this class, we've done some things that require calculators. We've done stability calculations. We've made buffers, and those involve natural logs and log 10s. So you'll want to make sure that you bring a calculator beyond a basic level calculator. So don't forget. I can't promise that there won't be any calculations on the exam. And if you've taken a look at the practice exam, you'll see that there are in fact calculations. So you could depend on there'll be at least one calculation on the exam. Somebody asked me during the study session yesterday whether or not you should be worried about memorizing all the Nobel laureates, because there were some Nobel questions on the practice exam, and I put them on the slides kind of as a reference, but I'm going to go ahead and tell you it's useful. And perhaps some of you may know where your group names came from, and I like to contextualize science and give credit where credit is due, but I'm not going to ask you to regurgitate the accomplishments of the Nobel Prize winners, the Nobel laureates for the exam on Thursday. I passed your quizzes back today. So one of the reasons why I do the amino acid quiz, other than to help you memorize the amino acids and make sure you memorize them before the test, so you're not spending the night before the test memorizing them when you should be practicing, or 2 nights before when you should be practicing higher order skills, is to give you a chance to practice for me, and then I can help you identify any misconceptions that you may still have left over. So some of you, if there were structural concerns with your peptide that you drew, I wrote you a note to come see me after class. Now, I think there was a really good participation at the practice session yesterday. So I went over peptide structure yesterday with that in mind. But if you got a note, come check in with me after class, and I want to make sure that we get you on the right direction for your studying from now through Thursday. So again, if you got a note, not a big deal, but just come check in with me and make sure that you're oriented for the next couple of days. You will have the opportunity to correct your quizzes for half credit. So if you missed 5 points, you have the opportunity to get 2.5 points back. Again, the goal of these quizzes is not to cripple your grade. Not that it would, because it's a very small percentage, but I more care about you getting the skills correct and learning the skills rather than being docked or punished or whatever for not having that skill quite down when you take the exam. So I want to give you the opportunity to practice and get it right so you can correct it for half credit. And, if you missed 1 or 2 points and you feel it's not worth your time, fine. But some of you may benefit from it, or you're the type of person who wants to get every single possible point back. And if you missed 1 point and you want to get 0.5, fine. If you turn it in correct, I'll give it back to you. But it's up to you. There's no pressure either way. What I'll ask that you do is that you make your corrections on a separate sheet, you staple it to the front of your quiz, and you turn it in when you come to sit for the exam on Thursday. So again, that's not a lot of time, but at the same time, it's going to help you study. So turn it in when you come in for the exam on Thursday. The exam sitting, that starts at 9. If you want to come at 9:15, fine. But I will give you the option to start at 9. And then just kind of reminder, things for our groups have gotten a little scrambled because we've had people dropping. Wouldn't say dropping like flies, but people drop sometimes starting class. As you know, you've sat in many classes, your sophomores, juniors, and seniors mostly. But just a refresher of the group tasks. The instructor and manager is responsible for directing the group and keeping everyone on task. The recorder keeps a log. So you're basically, the job of the recorder, I'm not giving you a separate sheet because I don't want to have you deviating from the coursework, but I do want you to keep a neat enough record that I can read it, and that you snap a picture of your work and you send it to me so I can give you feedback. So if there are any mistakes that your group has, I can catch them, and then it's an opportunity to steer you back on course. The reporter, you're the person who talks. And so in my groups of three, I've combined the reporter, and the reporter. I've combined those two, although I think perhaps for the next set of groups, I might combine recorder and reflector instead. Do you guys think that would be, are you guys happy with the recorder-reporter combination, or do you think it would be better to rearrange those in a different way for groups of three? Does anybody have an opinion on that? What do you guys think? Okay, all right, so for the next go around, okay, I should make a note. Let me get my planner actually. All right, now, because that was a kind of a thing that I did that was born out of panic because we suddenly had groups of three that I didn't know how to account for. Okay, so we'll combine instructor and recorder next time. And I realized that the way that this grid was set up perhaps might have been confusing, and that could explain for some of the reason why I haven't been getting marginal at best, not marginal best, but consistently I've been getting like 4, maybe 5 out of the groups turning in their recorder sheets, which, as you guys know, you're adults. If you want a full participation grade, you have to complete your roles. I realized that it might have been a little bit unclear. So for today, for the legacy of today, the recorder and the reporter are the same. So if you're in a group of 3, today and today only, I ask that you do both. And starting today, if you don't turn in the notes, I will take notes and it will come off your participation grade. If I've made notes in the past, I've erased them because I realized it may have been confusing. We'll start with a blank slate. But from now on, if you are in the recorder oh gosh, and I will walk it through. So those of you who are on the recorder slot today, I guess it is fairly clear. But Alex, you're the reporter. You're also going to be recording for today. So for today, and then next time, but I'll touch base with you guys again next Tuesday about what the responsibilities are. Just so we're on the same page. But yes, just a reminder, and we'll go through it again. And then we will also be rearranging groups next Tuesday. And I will also be writing up a survey. I will also be writing up a survey for you guys to evaluate your group members. And that'll be administrated. I don't know what platform yet, but it'll happen over the interwebs on your own time. Okay. Okay, before we launch into the actual stuff of class, does anyone have any questions? All right. Well, then let's go ahead and get started. Okay, before we touch base, okay, you guys did a pre-class assignment. The first question was a review from was a follow-up from last Thursday. The second 2 were questions that are meant to help you with your in-class work today with your teammates. Okay, so, and if you recall, we're talking about endopeptidases. Would one of my reporters like to remind the class of what an endopeptidase is? Alex. It's an enzyme that cleaves specific peptide bonds. So would another one of my reporters like to tell us some of the endopeptidases we've talked about to date? Yes, Addie. Right, trypsin and chymotrypsin. And one of those targets aromatic amino acids and one of those targets charged. Which is which? Okay, and so the way that enzymes work, as we'll see in the next couple of days, is if your substrate is, failing at drawing. If your substrate is an aromatic group, for instance, for that aromatic group to slide into the pocket of the enzyme and then have the C-terminal amide bond chopped, the inside of that enzyme pocket is going to have to be complementary to that amino acid side chain for it to fit and to be chopped. Okay, so for hydrochlorotherapy amino acid, what enzyme peptidase, what is the corresponding enzyme pocket going to look like if we want to accommodate an aromatic amino acid? Yes, Kiki. Okay, and why would that be the case? Okay, so the area around it might want to be small and perhaps thin, because the aromatic amino acid is kind of like a coin. I like to think of it as like a coin, so perhaps like a coin slot. But tell me a little bit more about the perhaps the polarity of the amino acid in that type, in that slot. What do they look like? Okay, what's your thinking first?
Probably also non-polar.
Right, so these amino acids are probably going to be non-polar. Some of them may be on the smaller side, like alanine or valine, but you may also have some larger aromatics in there as well, because as we're going to see when we talk about nucleic acids, and this is a term from organic, amino acids like aromatic amino acids like to do something called pi stack, where the pi bonds of where different aromatic groups can stack on top of each other and their pi orbitals will overlap. So there may also be some other aromatic amino acids in that pocket. Either way, it's probably going to be deep, it's going to be flat, and it's going to be populated by other hydrophobic or non-polar amino acids. How about our endopeptidase that targets a charged amino acid? What do you guys think about the lysines and arginines? What do you guys think about the shape of an enzyme pocket that's going to accommodate arginine or lysine? What do those two amino acids have in common? Okay. Yes, Elena? Okay, they're positively charged for one. And what else do they have in common, lysine and arginine? Yes, Grace? They're long and skinny. Okay, so we've got two amino acids that are long and they're skinny, and they have a positive charge on them. So what do we think that pocket's going to look like? Yes, Elena? So yes, so certainly the pocket, at least part of it, the part where that chart, where the end is going to go, is going to be negatively charged. But what about like the shape and the depth? I know, it's so early, guys. Yes, Janelle? Very good. So it's going to be small and skinny, because again, I like to think of the amino acid being like a hand fitting in the glove or the pocket. It's going to be long and skinny. And while there's going to be a negative charge at one end to attach the positive charge, the part where the carbon chain is going to be, it's probably going to be small and non-polar. Right? And so as we progress, as we moved into hemoglobin, and then a little bit today, but especially if we start talking about enzymes, we're going to be thinking a lot about enzyme pockets. So this is just an exercise in getting you to think ahead just a little bit. Okay, so what I'd like you to do is I'd like you to pull out your Foundations of Biochemistry book. The first exercise is to go and do problems 1 through 11. I actually have to run upstairs and grab my book, but before I do that, I'll run over and take your pre-assignment. But this is going to give you the opportunity to actually work through and digest what the binding curve of hemoglobin means, the oxygen binding curve of hemoglobin. So go ahead and get started and work on 1 through 11 with that oxygen binding graph. Okay? All right. Break that down. Or just say what? Okay, so what I want you guys to do really quick is I want you to send your reporters up to the board, and I want you to come to a consensus on problem number 2, which is what does the PO2 refer to in a solution like blood? And the blood, is there some O2 bound and some unbound? What form of the oxygen does the PO2 refer to? Reporters, come up. Put the minutes on this, what your group is saying on this, and then I want the class to find out the consensus. Groups, if you want to keep progressing and then catch up your reporters when they come back, that's acceptable.
I thought it was the other concentration sauce.
Yeah, no, that makes sense. Oh, and okay, so let's take a look at this. Okay. Okay. It says the amount of unbound O2 in blood. Okay. So let's take a minute and think this through here. So if we have a basic ligand binding curve where we have the substrate and micromolar, the phi, so the fraction of the sites occupied, and then we have a normal hyperbolic curve. What does the substrate concentration on the x-axis? Is it the unbound substrate? Is it the bound substrate, or is it the total amount of substrate in solution? Pardon? It's the total amount of substrate in solution, okay? So it's a similar thing when we have a chart for hemoglobin, where we have the PO2 on the y, the x, and the phi on the y. So does anybody remember from general chemistry what the state is of molecular oxygen? So O2, or O double bonded. Does anybody remember the phase of this guy? It's a gas. Okay. So oxygen is a gas. And so oxygen gets into our bloodstreams and some of it dissolves. So what the PO2 means, it's the particle of pressure of oxygen in the blood. So it actually refers to the oxygen that's like above the blood. But it turns out that the amount of oxygen that's in like the air in our blood is proportional to the amount of dissolved oxygen. But we can think of this as the total oxygen that's available. So it's not just the oxygen that's bound, it's the total amount of oxygen that's available, or it's proportional to the total amount of oxygen that's available to bind to hemoglobin. And that makes sense, because if we're plotting this So for hemoglobin, it looks like that. We want to track the amount of oxygen that's bound to hemoglobin versus the total amount of oxygen that's available to bind. Are there any questions on that? Is that clear? Am I getting nods? Okay. All right, proceed. I just wanted to clear that up before we moved on. Okay, all right. Proceed. Sometimes there's a lot of it. Yes, These examples, these questions are a little bit tough because they're a little more, qualitative, and they don't necessarily lend themselves to reporting on a board. But would one of my reporters like to take a stab at what their group came up with for number 11? So, how does the shape of this curve indicate a hemoglobin effectively delivers oxygen from the lungs? Somebody want to take a stab at that? Okay, Daniel.
So you said that transport and hemoglobin lungs that high concentration to it's got the higher the need for protein, the lungs tissue and the lower concentration.
Exactly. So one of the things you'll notice if you take a closer look at the binding curve, and I think it's pretty sure it's denoted in your book and your workbook, and also in the textbook and in the video, is they have shaded regions for the tissues and the lungs. And so if we remember, myoglobin's job is to bind oxygen, and it does a really good job. The hemoglobin does way more than just bind oxygen. It's an oxygen binding and transport protein. So it needs to be able to do versatile so it can bind and transport and release. And it turns out that the places where it's moving around the oxygen to or from, they correspond well to the relative concentrations. So in the lungs, there's a really high concentration of oxygen, and the lungs happen to be where hemoglobin picks up oxygen. So if we look at what the phi is in the lungs for hemoglobin in the blue, it's like a phi of almost but not quite 1. So it's going to be at any given time, most hemoglobins are going to be mostly saturated. But as the hemoglobin travels from the lungs, the PO2 is going to go down until you hit the tissues, where it starts dropping like a rock, and then once it lowers in the tissues, the hemoglobin's phi, so its number of sites that have oxygen bound, is going to start, I won't say bottoming out, but it's going to start dropping pretty steeply and pretty dramatically. And that's, at first, may look concerning, but it's not, because hemoglobin needs to be able to release oxygen so it can be picked up by myoglobin. So conveniently, this works out, and this cooperativity, or this funky sigmoidal shape of the oxygen binding delivery curve of hemoglobin works out so it can do its job. Okay? All right, so let's see. Next, let me pull up. Of course, it's going to be difficult, and it's not going to show up. There we go. So next, okay, so now I want you to think a little bit more. We have the two curves of hemoglobin and myoglobin overlaid in our in-class PowerPoint. And so I'd like you to answer questions 2. Some of you have already begun doing this. So go ahead and And I'd like to change the wording onto, I'd like to change the wording on 2C. Instead of smaller, I would say put tighter binding. Would hemoglobin or myoglobin have tighter binding? Seeing as I've given you the P50s or the oxygen equivalent of the KDs for oxygen. Proceed. Yes. Are you guys confused on two? Think bigger because both myoglobin and hemoglobin have binding sites, but myoglobin is a hyperbolic curve and hemoglobin is a symbolic curve. What about hemoglobin? Gives it a the right direction. I'm going to pull up a picture for those of you who are a little more confused, and that's okay. Let's do, okay. Here's the structure of hemoglobin. Okay, and I don't have a structure of myoglobin. We'll just pull it up as well. Oh, okay. How many globin folds does hemoglobin? Yeah, keep working. What's that? I thought you were raising your hand. Oh, no. Okay, groups, send up your reporters, and let's come to a consensus for B and C. Groups, you can continue, but make sure you fill in your reporters when they come back.
Oh, these like more cheese balls. Have you ever had the cheese balls? You know what I'm talking about? They were on sale at Target, and I was like, yes, please, please. And you can be succinct, that's fine. Very good.
All right, everybody. Okay, so, all right, so reviewing really quick, hemoglobin and myoglobin. So hemoglobin, so it turns out that hemoglobin's ability, yes, to bind and release oxygen, to give it that characteristic sigmoidal curve, comes from its quaternary structure. So, and I actually had a student last semester tried to debate with me about whether or not you could have, or this arises from cooperativity between subunits, and I had someone argue with me, and so I dug into the literature, and there are some obscure cases where there is cooperativity in monomeric proteins, but for the case of this class, where we're learning the foundations of biochemistry, for now, I'm okay with you making the assumption that in order for this to happen, you have to have quaternary structure. Myoglobin is a monomer. And whereas hemoglobin binds and releases oxygen, myoglobin just wants to hang on to oxygen really tightly because its job is to hang on to oxygen and store it for a rainy day, okay? And so it has what we call a hyperbolic curve. And if you have a simple protein whose job is to bind a ligand, it has one subunit, there's no cooperativity, you're going to have that curve. And in fact, on the ligand binding video, when you first learned about ligand binding, I showed you a hyperbolic curve because that's how we characterize basic ligand binding. A myoglobin, if you looked at that chart, you probably predicted, based off the structure and function of each, myoglobin would have a smaller KD, or I goofed in the problem, and it should be the P50, so apologies. It should be P50, not the KD. And that's because logically, for the jobs, that would make sense, because myoglobin's job is to bind and to hang on to oxygen. If hemoglobin had bound oxygen too tightly, it would not be able to release it when it needed to. So hemoglobin needs to bind it a little less tightly so it can more easily get kicked off. And if you look at that curve, you can see that this is the case. Because the P50 for myoglobin is 2.8 torr, the P50 for hemoglobin is 26 torr. There's an order of magnitude difference, or a tenfold difference between those two. And that makes sense based on what we want the different proteins to do. And you were correct in predicting that myoglobin would have a time. Now, does anybody, so we said, okay, so if you see a sigmoidal curve, you instantly think cooperativity and quaternary structure. Does anybody remember, do any of my reporters want to talk a little bit about cooperativity and what it means? Sure, Keegan. Right, so if you remember from the videos, hemoglobin can occupy, and I'm going over this because you're going to talk about it. I don't think I'm jumping ahead. Hemoglobin has two states, the R, or the relaxed state, or the T, or the tense state. So the R is going to favor oxygen binding, and the T is going to not favor oxygen binding. So when it's in the R, hemoglobin's more likely to bind oxygen. When it's in the T, it's more likely to release oxygen. So what happens is when you have hemoglobin that's bound to oxygen, it's going to be in the R. When you have hemoglobin that's not bound to oxygen, it's probably going to be in the T. And so when you bind one oxygen and have one subunit in R, it's going to become easier for the subsequent subunits to then adopt the R conformation and bind oxygen. Now, if you remember from the video, there's a bit of a debate whether or not when one binds, it flips the next one and so on and so forth, or if all of the subunits are in one and the other and binding just shifts the equilibrium. We don't really know. It's probably somewhere in the middle. But those are the two schools of thought. But the cooperativity is when you shift one subunit, it communicates to the other subunits and makes it easier for the other subunits to either bind oxygen or release oxygen, depending on which end of the curve you're thinking of your reference. So if you're binding oxygen, it's going to make it easier for the subsequent oxygens to bind. If you're releasing oxygen, it's going to make it subsequent for the other ones to be released. Okay, I'm going to stop jabbering. You guys keep moving. So why, what is it about this?
I think that's for this. So there's a reason why that would work for the city, and why it wouldn't work for Argentina. But why is that? Isn't that right? Okay. And so here's the signal what? So because we can not only because that means that even higher it's also and it may be that the one that's protein has a protein feeling yes, because since it increases at thank you. Oh, butter and donut hole. Oh, yes, that's yeah, I think that just as sometimes there is better morning like it takes us right. So if you were like so it binds yeah, so that's why it's why would so it does shuttle so that to be zero, it's small. So it may be pulled it totally like okay, so that's how you speak. Okay. So that's what I want you guys to do is I want you to draw new curve for the opposite one for the increase for the concentration. For the increase for the increase and then you have so remember the videos they're examples of how so like so it's still a sigmoidal curve, it's just depending on where it shifts.
Depending. So most of them, yeah, they're still sigmoidal, but there may be one where it's not. So like, okay, the Bohr effect. How when you decrease the pH, it shifts it in one direction. That's how I want you to think. That's what I'm wanting to see. Okay.
And you already have. And so that's kind of like, that's what's valid because I think it's all but I'm thinking more in terms of what's going to happen. specifically that last part. That's why I bought some oxygen. How are you guys doing over here? Okay, so on hemoglobin, where does oxygen bind? I think it leaves and then the other one, so proton binds which doesn't make it. Because the carbon dioxide binds. The BCC binds. Got it. Yeah. So I'm trying to create a table, but you can study from it, and then you can refer back to. Yeah, that's my goal here. Yeah, I'm trying to create a table where you can study. If that makes sense. Okay. We got a little bit off track. We have people staggered at different places. That's okay. It happens. But for you, there we go. For my peeps on the BPG problem. Okay. All right. Why did you flip? Okay, flip back over. Look at the structure within it. Where's oxygen bind? You're way what part of the protein is it binding? Right? Binds the iron and the iron. You would say that the iron is contained in the So then through the video and also in the book, there are very specific places because you're basically compiling a table and it's trying to start. And again, if you get stuck, I can help you, but that's kind of avoid that scatter out.
I think from watching the
All right, how are we doing over here? Lemmies, can I see your new curves? Okay, okay, that's fine.
we're just confused on it.
Okay, flip that, okay, so this is the new century, go. Okay, so you guys went the right way for proton, why did you do that? Did you get it, because that's what I showed you on the board? Okay. Right. Okay, so if you're favoring the T state, you want more oxygen to be released. So you're going to want to shift the curve to the right because more oxygen is going to be released than bound. Okay, that's cool. So you have two ones that favor the T state. So are they going to look the same or are they going to look different?
Lower concentration.
Pardon?
At like a lower concentration, so you like up here.
Not if you're favoring the T state. Not if CO2 and curve. Okay, so CO2 and BPG are going to look the same as protein because they're all pushing you. And that makes sense because when you're inside the oxygen, you're wanting to release the oxygen. Okay, so carbon monoxide. So you can go and you can draw with those other yeah, you could, but I'm not going to. Yeah, it could. Yeah, it could. I'm not going to make you differentiate between the two, right? I mean, you bought it and you feel like, in theory, if I had four, it's going to look at the right, right? But I'm not going to ask you to differentiate, really. I'm more concerned about trends. Okay. But if you have an anemic, let's say you can only saturate half of your body, And then what does carbon monoxide do that the other modulators don't do? So favorably are stable, but what happens with carbon monoxide? Carbon monoxide, it competes, so oxygen can't bind. Carbon monoxide bonds, blocks the hemoglobin to the R. That change gets transmitted to the other cells, and the other cell units get blocked in R. What happens if you block a cell unit R? It can't release oxygen. So your oxygen is just trapped. So what's going to happen to the shape of your curve if you're seeing carbon dioxide? But also think about the height of the curve. So let's say in both cases, if you have half of your hemoglobin down to CO, half of it down. So guys, we can start on a bit. Yeah. Okay. All right. So let's think about this. Okay. So you have hydrogen. So you have CO2 oxygen. It's still going to those down. Yes. So is it still correct? Okay. So these, you know that these guys get trapped. So if you were to shift your curve to the left or to the right, which of those is going to make more oxygen released rather than bound? Is this one going to result in more oxygen being unbound, or is this shift going to result in more oxygen? Pardon? Alright, so you have to think about, when you look visually, which of those is going to result in more oxygen? And then for carbon monoxide, what are those? When it binds, blocks that combination of bond, and then it causes all the other ones to be locked in the arms. Okay, so everyone think about, so if you shift your curve to the left, is that going to result in more oxygen or less oxygen? Okay, so you're So what happens? So this is, I'm not concerned about that. So if you shift your curve, that means there's going to be higher oxygen, wider range. Like all those like questions we have to like she's only covered like 3 or 4 topics all time and but like contracts. I just think
Okay. Okay. All right, everybody. Good work today. What we're going to do. So, not everyone had a chance to fill in your table. That's okay. So, what I'm going to have you do for your pre-assignment, part of your pre-assignment for next Tuesday, is check your curves against the book. Go read the book or watch the videos and find out where those specific points are. Fill in your table, fill in your charts. We'll touch base on those at the beginning of class. We'll also probably touch base on the hemoglobin conditions, and then we'll begin with an introduction to enzymes on Tuesday. I will post the pre-assignment as soon as I can, as soon as I am able to get that up. Again, exam on Thursday, and I'll see you then. Those of you who want to touch base with